Well, good afternoon, everybody. Welcome back to Network Security. So far, we are still talking about cryptographic building blocks. So in other words, we are still talking about data encryption algorithms. So before we start today's topic, do you have any questions for me? Okay, so let's refresh our minds a little bit. So we are looking at encryption algorithms, and so the ones we have looked at is Pseudo Cipher scheme, and then we have a concrete implementation of Pseudo Cipher scheme. So we got DS. And DS was a standard encryption algorithm used from mid-1970s to late 1990s to early 2000. And then at that time, DES was found vulnerable to brute force attacks. So either by special purpose computers or network computers. So then, of course, there was a need to have a more secure encryption algorithm for encrypting data for network communications. So then one easy solution is to have multiple DES. So instead of running DES once, you're going to generate several keys so that combine them, you get a longer keys, and then you apply DES multiple times. So the ones that's currently still in use is 3DS/3. Sometimes you can also see 3DS/2. Okay, so 3DS/3 means that you generate 3 different keys. You apply DS 3 times. Okay, so the common configuration you would do it is you do encryption first using the first key on a plaintext block, and then you apply decryption using the second key, and then you do encryption again using the third key. So the reason we do this is to maintain compatibility. So that means that we can still use 3DS/3 to decrypt ciphertext that was generated using single DES by making all these keys the same key, right? So K1 equals to K2 and is equal to K2 and is equal to K3. Okay, so we also mentioned last time that 2DS/2 is vulnerable to meet in the middle attack. So in other words, if DES can be cracked using brute force attack by checking all possible keys, that's 2 to the 56, then cracking 2DS/2 would only need a little bit more than 2 to the 56. So that's 2 to the 58, even though the key length is 112 bits long because you're using 2 keys. So 2DS is not secure. But then we are still not comfortable with this solution using 3DS/3 or 3DS/2 because since a single DS can be cracked, and people worry that somehow somebody will come up with something to crack this multiple DES. So that means we would really like to have a completely new design for encrypting data. So that's where advanced encryption standard came about. So this was adopted as data encryption standard in early 2000. Now it is the encryption, the default encryption algorithms we are using today. Probably for the next 10 or well, at least for the next 10 years, I think AES will still be around. After that, I don't know. We may still have, we may need some other algorithms, but for now, AES is the one. So, and also the different from DES is that AES actually is using more sophisticated computation. So that is depending, it depends on finite field operation. In particular, it takes a basic unit as 1 byte or 8 bits. So you operate on bytes, not operate on bits. So DES is you're operating on bits, and here you're operating on bytes. So we look at how AES encryption how AES encrypts data and how we can decrypt AES. Last time we also provide proof why this decryption works. Okay, so now this is our building block, right? So AES is the one that we will use when we look at security protocol for network communications. And we may also use 3DES/3 or 3DES/2. Okay, but then the next question we want to know is that how do we apply this encryption algorithm on a long message, right? So let's say I have a sequence of binary string. Let's say this is the original message we want to encrypt. So it's long, right? It's fairly long, much longer than 128 bits long, right? So you can, then the way to do it, of course, you gotta divide this M into blocks as we know it. So we gotta divide them into blocks. And at the end, if it's not long enough to make it into one block, you gotta have some padding using white space keys, for instance, and to make it a block. Right? All right. So then the next issue here is that do we apply encryption algorithm on each block independently? Or how do we just make it? So even for this simple thing, how do we make this encryption applying to these blocks more secure? So that is a topic of modes of operations. So now let's start my pre-recorded video on this topic. Okay. In this video, we are going to talk about how we apply a data encryption algorithm on a long message, on a long data. Okay, so the question we have is this. So let's say we have a very long data. We still use M to indicate this is our plain text. And then you either use DES or AES in trying to encrypt this message. This message is too long,
And DES can only handle 64 bits at a time, and this is 128 bits at a time. So that means we're gonna divide them into blocks, as we said earlier. We're gonna call it M1, M2, and so on. And let's say we have the last one. We call it, let's call it K. So the last one, padding may apply. Okay, so may need padding. Okay, so then let's say we have a encryption algorithm. Let's call it E. Okay, so also we have this K, secret key K. So this will be a building block. So to apply this encryption on each of these blocks, one simple way to do it is to do it individually. So it's going to be C1 and a K here. So let me put a K here with a little block. Oh, not block, maybe just K. So K, apply, and then this is E. So K, apply, C2, and then the last one, K goes in, we got CK. So then this will be transmitted one at a time to the receiver. So then C1, so C1 goes to the receiver. So this is the receiver in network communication, and then go to 2. So the order is C1, C2, CK. So this is the easiest way to apply a data encryption algorithm. But then the problem here is that, oh, by the way, this is called electronic code book mode. Electronic code book mode. So this is the mode of operation. We call it ECB. So the problem here is that if in the plain text, let's say this is MI, this is MJ. If MI is equal to MJ, then CI and CJ here will also be equal. So we generate CI, CJ. So if MI is equal to MJ, then CI is equal to CJ. So the attacker using a network tab, using a sniffer, then can find out in this message, in this CI is equal to CJ, so which infers to the structure of the original message, which can be used to assist deciphering this message M. So this is not good. So such situation is not what we want. So then we know ECB is straightforward. but it is not that good, because if there are two blocks that, or more than two blocks that are identical in the original message, then the ciphertext blocks will also be the same. So that infers the structure of the original text. So how do we fix it? So let me remove this and move on to the next slide. Okay. So let me remove this. And then we move on to the next slide. Okay, so we already looked at the Cipher blockchain mode. So to overcome the, I'm sorry, we already looked at electronic code book mode. To overcome the drawback of electronic code book mode, the way we do is to use a Cipher blockchain mode. So let me start a new screen. To illustrate this idea. So as we have earlier, so your long data is divided into blocks. And the last one is MK. Originally, this is what we have. So we got K. And this is C1. This is EC electronic.
By the way, so this K here is a number of blocks. I probably should use N, because I don't want this K to be the, I don't want to give the confusion to you that these two Ks are the same. So this K is just the number of blocks, and this K represents a secret key. Okay, so I hope that you can make that distinction yourself. Otherwise, you're going to put this using a different symbol.
Code book. Going there, C2 and so on. So now we want to fix the problem that we mentioned earlier. So what we want is to hide the structure, even though you may have two blocks in the original plain text that are identical, but the ciphertext will not be the same. So the idea then is I am going to use the previous ciphertext block to be part of my encryption. So what I'm going to do now is this. I'm going to use an initial. So this is the initial ciphertext, could be all zeros or just some initial value. So before I apply this algorithm, encryption algorithm, I first change M1. Okay, so then this now goes to encryption. So my key goes in here. That's C1, and then C1 will go. So C1 will go exclusive or M2, and then I apply encryption on this result. We got C2, so the key goes in. So you do the same on M3. E key goes in. C2, oh, C3. So last one will be, so this is CK minus 1. E K goes in. That's CK. So the transmission direction is C1, C2, C3 until CK. So this way, even MI is equal to MJ, because their structure has been affected by the previous ciphertext. And so this will not, so the ciphertext will not be the same. Okay, so this is called cyber block training mode. Cipher block training mode. Excuse me. Cipher block. Cipher block chaining mode. And call it CBC. So the training part is because you are using the previous ciphertext block. Okay, so and now there's some issue is that if during transmission, okay, if during transmission CI has an error, okay, there's an error, which means that it's transmission error, then of course we know MI will be infected. Will be affected, sorry, not infected. We're not talking about virus here. We are talking about getting the correct MI. So this will be affected. That means the correctness and correctness of MI will be affected because CI, when we apply decryption on it, that will be affected. Oh, by the way, the encryption is CI, which is EK CI minus 1 exclusive or MI. And then the decryption will be decrypt CI and then exclusive or CI minus 1, which will be MI. Excuse me. Okay, so this is I from 1 to K. Okay, so if, as you can see here, if CI has an error, MI will be affected because this part is not going to be correct, but then it will also affect because you're using CI minus 1. So M sub I plus 1 will also be affected. Okay. So that is a little drawback. Okay, so we are going to see how we can reduce the error, reduce the effect of transmission error using counter mode. So let's come back to this. Let's just go back and let's go to counter mode first. So the counter mode is like this. Okay, I can just draw it here now. Should have enough room. So so we are going to feed this block. So initially we maintain a counter. Let's say this is a counter. So initially we have an initial value CTR 0. But let's just say this is a counter. So let me remove that 0. Okay. You know we have an initial value to begin with. Okay, and then I'm going to increase this value. Okay, so I'm going to increase, sorry, I am going to, so whatever the values here, I am going to, let me remove this part, let me remove this arrow. Okay, so I'm going to encrypt this counter. So that means whatever the value goes in, I am going to encrypt it. So using K. And then whatever value here, I'm going to use it to do a simple exclusive OR with MI. So that gives me CI. Okay, and then I'm going to increase it by 1. Okay, so this goes first. So this goes first. This goes to second. After this is done, I'm going to increase this value. That's 3. Okay, so this I from 1 to K. So as you can see here, at the receiving side, it will start the same initial value of this counter and following this procedure. So
Professor?
The
Yeah.
encryption is...
Yeah.
So it mentions for the counter, starting from an initial value. As an example, would we start from 0 or would we start from some random value like 15 in binary?
As long as both sides will start from the same value, doesn't matter which one.
It doesn't matter. Okay.
Yeah.
All right.
So in other words, they have to build in the protocol. Okay, so when you use counter mode, they always start with the same counter value. So that way your decryption will make sure, otherwise it won't. So so this initial value has to be the same, either all zeros or all ones or some kind of other values. They'll be fine as long as they are the same.
Okay. And then you mux them.
And then you encrypt the counter.
Yeah.
Then,
okay.
Yeah.
All right. Thanks.
Sure.
you encrypt the counter, and after encrypt this counter, you increase the value of counter. So that's after. So the value, the encryption is exclusive or MI. So the decryption is that you use decryption here. So this is decryption. Okay, start with the same counter value. You decrypt the counter value, and okay, and then you exclusive or CI, which is what you received, and then you get MI. So you, as you can see here, if there is a transmission error, say in CI, then only MI is affected. Okay, so this counter mode has this advantage. So both.
I need a so this should still be EK. So in other words, what we do here, so it's not decryption. So what we are trying to get here is that when we get CI, we want to get MI back. So what we do here is that we do exclusive or EK of the counter at both sides. Then this EK counter, because they are the same, so these are the same, so they become one. They become zero because they are the same. Exclusive or of the same thing is zero. Then you get MI. So the original one is right. So cross that D out.
Both Cbc mode and CTR mode are commonly used. All right, so let me remove this. And we go back. All right, so there are other two modes. One is called Cipher feedback mode. Then the other one is called the output fields. Cipher feedback mode. The other one is the output feedback mode. So these two modes, modes of operation, are similar. Okay, these two are similar. So what they really want to is to generate stream cipher from block cipher. Okay, so and in combining CBC. So let me okay. So let's say you have a block cipher. Let's say you're using AES, it's 128-bit long. It's AES. So after AES, what you are getting is also a 128-bit string ciphertext. So this is what M. Okay, so but what happens if I just want a stream? I just want a character long ciphertext. So that is called stream cipher. Put it here. Stream cipher. Okay, so the way then we can use a part of it to do encryption, and then this part, whatever the value, so we're going to shift. Okay, and then this will be added to the back. So the next round, we are going to look at this part, right? So just keep shifting for a certain number of times, depending on how long right? Your ciphertext would be either 8-bit long if you're using ASCII, or 16-bit long if you're using Unicode, or in any situation you could just have an S-bit long. So depending, so of course 128 has to be divisible by S. Then whatever that the result of that division will be the certain number of rounds you want to carry out this operation. And in some kind of a CBC mode, cyber block training mode, for each substrings, okay? So here, we also use the initial vector V0 because we're using CBC. And we are going to encrypt, okay, this the initial vector, I call it UI, and then I'm going to, so this is a prefix, so this is S-bit prefix, so we get the prefix here, and then your block will go into here, so let me draw it better. Okay, so we have S, and then what we're going to get is let me remove this too. And then so this is sort of like a counter mode thing. So we first has this VI minus 1, and then I'm going to encrypt it. Encrypt this one. I get U sub I. So this U sub I, I have a prefix. So this is S-bit long prefix. And I directly use this to exclusive OR your first byte, WI. Okay, so that gives you CI. Okay, so that's where this for. And then now I need to update the next one, the VI. So VI, then I'm doing to a shift. I place the CI, so now I'm going to shift to the left. So that will be this part. So the suffix shift, and then place the CI in here. Okay, and that's my UI plus 1. So then you repeat this until your block is done. Okay, so so this is the decryption. This cipher feedback mode, and the next one. Okay, let me move this first. Erase this. The next one is output feedback mode. Is about the same idea. Okay, so as you can see, this step is the same, but the only difference here is The only difference is here. When you update your VI, so instead of filling in, now before we are filling CI, filling in CI, but this one is a circular shift. But this prefix is after the encryption. So without using ciphertext, it's after the encryption, you change this part. It's not circular shift. I take it back. So this is, instead of using CI, you are using this to fill that one in. So that's the only step that is different. Okay. With this, we know now how we can apply a data encryption algorithm on a long data. There are other ways to apply encryption algorithms, but as I said earlier, the CBC mode, cyber block chaining mode, and the counter mode are commonly used. Okay, so, and that is the end of this video.
Okay, so once we know how to apply an encryption algorithm on a long data string, so in order to use data encryption, the next thing is we have to generate secret keys, right? So the next thing is how do we generate, how to generate secret keys. That's the first thing we want to know before we can deploy these encryption algorithms to secure packets, right? Data communications. And then the second question is how to distribute secret keys. Right. So you generate secret keys. I want to encrypt a message and send it to you. Now, how do you know which secret key to use? How do I send my secret key to you? So that's a question, right? So obviously I need to encrypt my secret key too. Now, in order to encrypt something, you gotta have prior shared secret, but in network communications, we cannot assume that happened, right? So you talk to somebody you may not even know. So how can you have prior secrets? You cannot, right? So then of course we have to come up with some kind of mechanism so that you can distribute secret keys securely. So that will be the topics we're going to talk about in the next module. So now I'm going to the key generation first. And then we're going to look at key distributions.
So this is the first video of the next chapter, or?
No, this is the first video in module 3.
Okay.
Yeah. So in other words, differently organized from your textbook. The textbook chapter 2 is all about data encryption and key generation. And chapter 3 is about key distribution. Now I want to put things about keys in one module. So this module we have key generation. Module 3 have key generation and key distribution. And then we'll also talk about authentication in chapter 4. Okay, so now let's look at this key generations.
We have now looked at data encryption algorithms and how to use data encryption algorithms to encrypt long messages. The other part that we haven't talked about is how to generate a secret key. Secret keys are the most critical components of encryption algorithms. The best way to generate a secret key is to use is to generate it at random, but of course we know that there is no such thing as true random, true randomness in network security. So we are going to use a pseudo-random number generator to generate a pseudo-random number. And because what we are really interested in is a string, so we are going to use a pseudo-random string, to be our secret key. But then, as we mentioned in one of the earliest videos, that number it can be thought of as a string, and string, if it begins with a digit 1, a binary string, if it begins with a 1, then of course it is also a number, integer. So we are going to use pseudo-random number generator to generate a secret key of a desired length. Okay, so the two pseudo-random number generators we are going to talk about are the following. The first one is ANSI standard. It's called X9.17 pseudo-random number generator. The other one is called BBS pseudo-random bit generator. Okay, so so the first algorithm generates a pseudo-random number of a desired length. The second is a pseudo-random bit generator. So it generates a random bit, okay, one at a time, like flipping a coin. Okay, so you flip a coin, you can either end up with 1 or end up with 0. Okay, so so this BBS pseudo-random bit generator has good statistical property that we're going to mention later. The ANSI X9.17 pseudo-random number generator was published in 1985 by the American National Standard Institute, ANSI, for financial institution key management. So for the banks, basically, for banks, okay, for bank transactions. It was based on 3DS/2 with two initial keys, K1 and K2, and an initial vector, V0. And it uses two special 64-bit binary strings, TI and VI. The reason you use a 64-bit is because DES takes 64-bit block as input and also output 64-bit ciphertext. here, okay, TI represents the current date and time updated before each round. And VI is called a seed value, and it is determined as follows. Okay, so this subscript I depends on denotes the i's iteration. Okay, so I starts from 0, 1, and then it keeps going. So so that means initially I have a initial vector v 0, the initial time t0, which is the current time, and it uses two secret keys, k1 and k2. So these are initial keys, and these initial keys can be generated either on a passwords, or it just enters 64-bit string. It just create two 64-bit string. Okay, so so now it uses 3ds/2. So the way to do it is encryption using K1, decryption using K2, encryption using K1 again. So this notation means the way how we apply DES. Okay, so you encrypt TI, the current time, and then exclusive OR with the seed value VI. So initially it has a seed value, and then you encrypt it again, okay, using EDE with the same key, K1 and K2, which means that you encrypt this part using K1, and the result will be decrypted using K2, and then the result will be encrypted using K1 again. That gives you RI. So then RI will be used as a seed value for the next one, for the next iteration. So TI is the current time. You basically do the same thing again. And then you exclusive OR with RI. So RI is this whole thing. You can place it in here, and then apply 3ds/2 again. So then your random value will be R0, R1, and you can keep on going. So if you keep running this algorithm, then you keep generating 64-bit pseudo-random string one at a time. Okay, so you get R1, that's the first random number. I'm sorry, R0 is the first, and then R1, R2, R3, blah, 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 keep on going. The BBS pseudo-random bit generator is done as follows. First, let P and Q be two large prime numbers satisfying the following equality. So P modulo 4 is equal to Q modulo 4, which is equal to 3. Okay. For instance, I think P is equal to 11, so 11 mod 4 is 3. Okay, 11 is a prime number, and so what would be the next one? Like 23, when Q is equal to 23, and 23 mod 4 is also equal to 3. So 23 is a prime number, right? So you can, for instance, you can take P equal to 11 and Q equal to 23. So these equalities are satisfied. And then we let N be the multiplication of P and Q. Okay, so we sometimes call this number N a semi-prime because it is a product of two prime numbers. And let S be a positive number, so which is the initial seed value, such that S and P are relatively prime, which means that the greatest common divisor of S and P is 1. Okay. For instance, if we pick, so let's say P is 11 and Q is 23. So, let's see, if S is, you want to be 11, so 12 obviously satisfy this, but if it's a 23 and 12, that also satisfies the GCD of 12 and 23 is also 1. Okay, so S is relatively prime to P and S is relatively prime to Q. Okay, so once we have these three parameters, we can generate random bits, pseudo-random bits as follows. So the first random bit x0 is equal to square S square mod n, and then you keep on squaring the result mod n, right? So xi then is equal to xi minus 1 square mod n, okay? And then your bit will be xi mod 2 because now it generates either 0 or 1 a bit. So bi is equal to xi mod 2, I starting from 1, 2, and so on. So that is how a random bit is would be generated. Now this is a pseudo-random. It's not a it is not truly random. It is a pseudo-random. Okay. So this BBS pseudo-random bit generator has a good property, namely predicting the I plus 1's pseudo-random bit b sub k plus 1 from the k previous bits, right? Suppose you keep a history of the previous bits you generate, and then based on what you know about B1 up to BK, you want to predict what the next pseudo-random bit is. That's B sub k plus 1. And predicting the correct bit, it's hard if integer factorization is difficult. Okay, so integer factorization means the following problem. So you are given an integer n, you want to find out a factor of n, a non-trivial factor. Non-trivial means that the factor is greater than 1 and not the number itself. So you are given n, the non-trivial factor will be a number m. M is greater than 1 but less than n. Because if n is a prime number, you don't have a non-trivial factor. So in general, given any integer number n, you want to find a non-trivial factor. And the algorithm for doing so, the best algorithm we know is is exponential time algorithm. So that is hard. Okay, so this means that at the current knowledge, okay, about integer factorization, you want to predict the next pseudorandom bit based on what we have seen. So what we have generated so far is hard. Okay, so which is good. So just look. So it looks like very random, right? Because before you flip a coin, even though you have observed your previous coin flips, you want to pick the next one, you still don't know. You still don't know for sure what would be the next coin flip will be. Either 0 or 1, but you don't know which one. Okay. And so this just means if integer factorization cannot be solved in polynomial time, then a BBS pseudorandom bit cannot be distinguished from a true random bit in polynomial time. Now, the fastest algorithm we know at this time that solves integer factorization has this time complexity, which is exponential. Okay. The last bullet, so this is a comment. Using a quantum computation model, okay, so I put a theoretical model here because we don't really have a functional real quantum computer to do this. It's just on a theoretical quantum computation model. Integer factorization can be solved in polynomial time. Okay. So which means that under this quantum computation model, you can predict, okay, what the next bit would be with good probability based on what you have generated. All right, so that is how, so we have talked about two pseudo-random number generator. So the first one is ANSI standard. So we can use that by using 3DS/2. We can generate secret keys of 64 bits long. If you want to generate a secret keys of, let's say, 128 bits long, you can either use this ANSI 9.17 standard twice, right? So we just use RI and R sub I and R sub I plus 1. Concatenate them together, then you can get a 128-bit long key. Or you can concatenate another one and another one, right? So then you get a longer key. So this is one way to generate a random key. And the other way, using this ANSI standard, is to change encryption, okay, using just AES, right? So this algorithm using 3DS/2, of course, that just means an encryption algorithm. Of course, we can use AES alone, right? For instance, we just replace EDE sub K1, K2 with AES sub K, right? So you replace this AES sub K, replace that with AES sub K. Same thing for these two. Then you can also generate a secret key of 128 bits long. Okay, and to use BDS pseudorandom bit generator, so you repeat this for 128 times, then you can get a 128 bit keys. Okay, so this generates 1 bit at a time. All right, so that's the end of this video.
Okay, so now what? So basically after this, then we have concluded chapter 2. And however, we still have a second question we need to answer, which means that after we have this key generated, and how can I distribute this key secretly from my end to the other end, going through the internet without being seen, right? So you don't. So that means that I have to come up with some mechanism somehow to encrypt it without using prior secrets. So that is the topic of public key encryption. So now let's start public key cryptography.
So now we are going to look at the issue how to transmit secret key from the sender to the receiver in network communications. Okay, so let's assume that Alice has a file to send to Bob. Okay, but Alice doesn't want anybody else to read M except Bob. Okay, so that means now Alice wants to use, let's say, use AES encryption algorithm to encrypt M using a secret key K. So Alice knows. So Alice knows how to generate K using ANSI X 9.17 standard or BBS pseudo-random bit generator, to generate a 128-bit key. Okay, and she also knows how to use Cbc mode of AES to encrypt K. So that creates a sequence of cybertext blocks. So then Alice wants to send this. Let's say, so this C1, C2, CK, CNs really is the cyber block of M. So each of these is 128-bit long. So that means now C1, CN, okay, so Bob gets these cybertext blocks, but Bob cannot do anything about it because Bob doesn't know K. Bob doesn't know. Okay, so that means Alice needs to send over this K as well. So then the question is, how can Alice send K over to Bob secretly? Oops. Without sharing private, without sharing prior secrets with Bob. Because in network communications, most of the time, we would need to send messages to strangers that who we don't know. For instance, when we do online shopping, so we want to send in our credit card information. We don't want anybody else to see that information, so we will need to encrypt that credit card information and send it to the merchant on their website. But then we don't share any prior secret that I don't share any prior secret with that merchant that I can use as a secret key to encrypt my secret key, right? So that is a challenge. Okay, so Alice needs to send K over to Bob secretly. So that is the first task. The second is that Alice doesn't share any prior secret with Bob. So that so there is no prior secret with Bob that can be used to somehow encrypt this K. So what can we do? So public key cryptography PKC was invented to solve this problem. To solve this problem in the 1970s. Okay, so this is it allows key distributions, secret key distributions, secretly without sharing prior secrets, and it can also be used for digital signature. That is authentication. Okay, so it's commonly used as digital, is commonly known as digital signature. All right. So now let's look at the idea of PKC. So basic ideas of PKC. So there are two ideas. So let me talk about the first one. So let's imagine in a postal service. Okay, so Alice wants to send a message M to Bob. And without, so Alice wants to send M to Bob such that nobody else can see M. So the normal method of using an envelope to seal M in it is not
Okay.
secure because
So the time is up, so I will stop here. So we'll continue this topic tomorrow. So before we end today's lecture, so do you have any questions for me? Okay, then I'll see you tomorrow. So bye-bye now.